And these are the laws by which we, technically speaking, we do evaluate limits directly without having to use a table, the way we might put that. And it turns out limits, as far as these limit laws, are very nice. I'll just put number 1 up here. If you've got the limit as x approaches a, f of x plus g of x equals the limit as x approaches a, f of x plus limit as x approaches a, g of x. Okay, what this is saying, just for a hypothetical here, and we'll go all the way through one using these limit laws, but by limit law number 1, it says that if you've got two things added together, you can break those down separately and evaluate the limit of the first, and then to that do the limit of the second, and then add those together, add in between. That's very nice, okay? That enables us to do, with the rest of them, it enables us to do a lot of different things, but they're pretty straightforward. The limit, if you've got a sum, the limit of the sum is the sum of the limits. What's number 2? The difference. The limit of a difference, number 2, is the difference of the limits times number 4. Number 3 is a constant. You can pull a constant out. 5 is division, so you can break up division. So all this is saying is you can break up a limit into the component parts nicely. Not always can you say that. We'll look at some stuff where you can't do, usually adding and subtracting you can, but when it gets to multiplying, dividing, that's not always as straightforward, but with limits it is. I was just going to show you here what this is. Say I've got the limit as x approaches, say 4 of x plus the square root of x. Basically, by law number 1, what this says is I can do this, the limit as x approaches 4 of x, then do that, the limit as x approaches 4 square root of x. That's what limit law 1 allows me to do, and you can see the advantage of that because the limit as x approaches 4 of x, that's going to be 4. The limit as x approaches 4 of the square root of x, that's going to be 2. 4 plus 2 is going to give you 6. Okay, so yeah, this is the process. We won't always necessarily break it down as much as this, but that's the idea on these limit laws. These are very nice, cut and dried limits. Basically saying just about for anything on a limit, you can break it down. Now the one exception is on the dividing. This one's number 5, skipping ahead there. The limit as x approaches a, f of x of g of x, it says, yeah, you can split those up. Do the limit of the top divided by the limit of the bottom with one restriction. Doesn't it say the restriction? If the limit x approaches a, g of x does not equal 0, why would we have to throw in that restriction? Well, if the limit as x approaches a of g of x is 0, we've got ourselves an undefined, don't we? This expression would be undefined. So there are a few restrictions. Number 6 has a restriction, n is a positive integer. Now, along about 7 and 8, that gets kind of to where the rubber meets the road, as we say. Yeah, if you've got the limit as x approaches a of c, and c being a constant there, it says the limit as x approaches a of c is c. Well, that's just saying if you're doing something like x approaches 5 of some constant 15, well, as x approaches 5, does this value change? No, it's always locked in to be 15. So that's all it's saying. The answer there is 15. Number 8, the limit as x approaches a of x. Oops. The answer is a there. Well, that kind of gets back to one we just did. That was kind of hopefully obvious. If x is approaching a and your expression here is x, well, x approaches a, so the answer that x is of course a. So anyway, it's pretty cut and dried. And then throw in a power, limit as x approaches a of x to the nth power. Well, then it's going to be a to the nth power is your answer there. So anyway, and there's 11. 10 and 11 are kind of the roots, but they're nice. You got the limit of a sum, it's the sum of limits. If it's a limit of a difference, it's the difference of the limits. If it's a limit of a quotient, then it's the quotient of the limits, provided the bottom's not 0. All very nice. All right, so now that you've seen those, here is, well, number one thing we're going to do with that anyway. We'll just do this, we'll actually just kind of do this once or twice maybe, but here's what this enables us to do. Say I have the limit as x approaches 3 of x squared minus 3x plus 4. I kind of already hinted at this maybe a day or so ago, sometime last week. But here's what the limit laws enable us to do. Here's my instructions. Evaluate this limit and justify each step. Like I said, we'll just do this once or twice with this justifying. What I mean by that is take these limit laws that we just talked about on the handout and justify what we get to be the actual limit here. Because step one would say, well, by which limit laws can I do this? Limit as x approaches 3 of x squared minus the limit as x approaches 3, 3x plus the limit x approaches 3 of 4. What limit laws enable me to do that on the sheet? The first and second ones, right? Limit law 1 and limit law 2, LL1 and LL2, enables me to do that because limit law 1 says I can split up a sum. Limit law 2 says I can split up a difference. Well, I've got kind of both there, doing them all at once, but yeah, I can split up a difference and I can split up a sum. So limit law 1 and 2 allow me to do that. Now, now I can work on this one. There is a limit law that enables me to skip right to this. The limit as x approaches 3 of x squared is 3 squared. What limit law would that be? Limit law 9? Yeah, if you've got x to a power, then your limit goes to, that number to the power. That's limit law 9. Okay, maybe a couple. I don't see one that allows me to go directly. So by what law can I do this one? See, one that I can break this one up. I can bring that 3 out by which limit law? Limit law 3, okay. Yeah, limit law 3 would allow me to do that. And then this one, I can go directly to the answer here. What's the answer here? This part. Well, it's limit of a constant, which is just the constant, isn't it? Which that's 7. And then, last but not least, then we have 9 minus 3 times 3 by limit law. That'd be limit law 8, wouldn't it? This is our A, so the answer goes to A there. So, yeah, get 9 minus 9 minus plus 4, sorry, which is 4. Okay. All right. It's good to see that at least once or twice. And I think I have one of the homework problems where you have to do that. But here's the good news. Question? Yes. Yes. Brought this one out. Yeah, by limit law 3, this constant in front there, by limit law 3, it says I can bring that out front. Any number constant. Yeah. All right. So here's the good news, though. Good news was, and I think I stated this last week, is what did we wind up doing here to evaluate this limit? If we look at it just as a kind of a short and sweet problem here, when I went kind of from this step all the way, and let's say I jump to this step right here, basically what did I do here in my original function? How did I get from that limit to this step right here? Substituted, right? I just substituted x to be 3 here and here. Of course, plus 4 is the constant. 3 squared gives me 9. 3 times 3, and then plus 4. I substituted. As I stated, I think last week, yeah, a lot of times this is what we're going to be shooting for, is breaking it down to where the limit I can substitute in. I can substitute the values in. Now there's a lot of behind the scenes going on, and from here on out, besides that one homework problem, we're not going to have to justify each step. But there are, just wanted you to know, there are limit laws that allow us to do this. You always want to have some type of law to justify your step there in mathematics. And there are, okay? But the good news is we can just use substitution. Substitution is allowed on polynomials, algebraic expressions. You're taking the limit of, if you can, okay? But here's the thing. You know, if I had limit as x approaches 5, x minus 6 over x plus 3. Same thing holds true for this. We could go through each step-by-step limit law and do that, but can I substitute here? Yes, I can. There's not any problem here with substitution. So unless it says justify your steps, if you can substitute, substitute. You don't have to go through all the limit laws here. So I can. 5 minus 6 over 5 plus 3, that is going to be your limit. negative 1/8. The problem, though, comes in because here's what we run into. Say I had the limit as x approaches 2 of x minus 2 over x squared minus 4. I run into a problem there. Can I substitute here? No substitution here yet, anyway. Why not? Why can't I substitute? Yeah, if I plug in x to be 2, I get 2 minus 2 over 2 squared minus 4. I get 0 over 0, undefined. Yeah. That is exactly what you're going to run into on most of these, starting out with anyway. You're going to run into it, an undefined expression if you substitute. So, what we have to do is we have to work around that. Here's how we're going to do that. We're going to use several different techniques to get around this. I mean, we used tables in the past. We're going to use a little more direct route, more algebraic route, we might say. And this one is an example of the first type of technique we're going to use. And that technique is by factoring. Sometimes we can use factoring to solve or evaluate these limits. So that's technique 1. You see here, if I factor the bottom, difference of squares, how does that factor up? Well, this would be x minus 2, x plus 2, wouldn't it? X squared minus 4 is x minus 2, x plus 2, factoring. And I guess maybe we'll call it factoring and canceling, because once I get it factored, can I cancel there? Yeah, and the thing of it is, you know, here, x minus 2 is definitely a factor of the original, but we are approaching 2. And so taking this factor of x minus 2 out, what it takes out is that undefinable part of it. But the thing is, we're approaching 2. So when we're approaching 2, it doesn't really matter what happens at 2. So taking out that piece doesn't affect this limit at all. And matter of fact, it allows us to actually evaluate this. That gives me, because I can cancel the x minus 2, I got one on top, one on bottom. That leaves me with this, doesn't it? So what's the story on that then? Can I substitute now? Yes, I can. Yes, I can. Now I can substitute x going to 2. Well, that doesn't create a problem, x being 2 now. And so we get 1/4. See that? So factoring and canceling, you can do that on these limits. So that's one thing we can utilize here. And you might note here, does this limit look familiar? I guess that was a couple times ago. We did that limit with a table. And didn't we come up with 0.25 from the table? Well, here's verification of it, more directly, algebraically speaking. Okay? All right. So here's another one. How about limit as x approaches 5, x squared minus 5x over x squared minus 8x plus 15. Can I substitute there? Well, just look at the bottom. Bottom would be 25 minus 40 plus 15. The bottom is 0. So we can't substitute. You run into that a lot. Okay? So what do? Well, we do a little bit of factoring. Now let's factor what factoring you see on the top. Pull out an x times x minus 5. Bottom, factors, trinomial, x and x. 5 and 3, both negative. Negative 5 minus 3. Yeah, so that does allow me then to cancel. The x minus 5's out, cancel.